Well, welcome to All Space Considered, everyone. I'm Dr. David Reitzel, and this is All Space Considered, and it is the third Thursday of the month today. By the way, I'm laughing about the music. Somebody on our YouTube chat already wrote, "Is this Hannah's doing?" And indeed, I think that was Hannah's doing, and it was just fantastic. She's the Ennio Morricone of our staff, I guess. All right, there we go. I somehow switched off my thing. So, as today is Thursday, June 15th, 2023, and we are going to do a show kind of all about binary stars, or were they binary objects, things like that. And we have a very special guest with us, Dr. Devin Chu from UCLA. He's an astronomer at UCLA. So, thank you, everyone. We will have our sky report after that, as always, with Patrick. Patrick's here with us tonight. A pretty picture, I guess. Oh, we can applaud for everybody. Why not? And we will have a very short video break of some pretty pictures that we've put together from some of the very talented amateur astronomers that send us some wonderful, wonderful pictures. And then for the second half of the show, we were going to have a section, History of Seeing Double, although we have to cancel that segment tonight. Hopefully we will record it for you and post it to our YouTube channel so you can take a look at that later. But then we're going to turn to Will It Merge Black Holes with Vanessa, of course, who's going to talk all about that. So merging black holes. And how do you say your last name? Alarcon?
Alarcon is fine, yeah.
I want to make sure I get it correct. So exactly. So one of our new presenters on the stage with us. And then lastly, well, not lastly, but we're going to have Out to Launch with Jared. We're going to talk about some of the launches that happened. And then I will close out the show with binary briefs. It's a few different stories about some binary objects, and they're a little bit unusual, so I'll talk about some unusual objects. But to thank you. Thank you so much. And one last time, I'll give you a last chance to applaud. Tonight's show is brought to you by the City of Los Angeles and the Department of Recreation and Parks, who own and operate Griffith Observatory. And as always, we like to thank Griffith Observatory Foundation, who is our exclusive nonprofit partner. And we thank all the members and also all the individuals that have made a donation, and also all the people who have given us grants for our programs as well through the foundation. So thank you. Yay, one more applause. Well, moving on, I thought, well, we're doing a show about binaries or twins, perhaps. Does anybody recognize this constellation? That's Gemini, believe it or not. That's the constellation of Gemini, the twins. And believe it or not, that was my sign growing up, of course, which you might think, oh gosh, he's talking about signs and he's an astronomer. Well, they have an astronomical origin of sorts. It's where the sun is on your birthday originally is what it was. And of course, this is the constellation of Gemini here, the twins. And I always thought I was a Gemini, but our meridian arc here that's in our Gottlieb Transit Corridor here at Griffith Observatory, it's an instrument that measures the moment of local solar noon, by the way. It also has marked on it constellations and dates. And it indicates which constellation the sun is in on a particular day. At local solar noon, a spot of sunlight moves across that arc, illuminating some sensors in the middle, and it lights up the constellation on the star chart. And on June 11, as you can see there, well, that is Taurus. I always thought I was a Gemini. So what's going on here? Gemini doesn't start, it looks like, till about the 20th of June. So there are others out there, I'm sure, that are also Tauruses. So yeah, why? What's going on here? Well, it's on the right-hand side already. What am I doing? I'm losing my mind. This all has to do with precession. The Earth's axis, every 25,800 years, does one wobble like a top. And it's because our equator is a little bit bigger. It's bigger around at the equator than it is pole to pole. We're a little bit of a squished object. So as the moon orbits around, it applies a little bit of a torque. That torque causes the Earth to precess, and it scribes out that motion. So Vega will be our North Star in, 14,000 years, something like that. So Polaris won't always be our North Star, and that also means the constellation that the sun is in on any given date moves, and it changes. So from the couple of thousand years ago when the twins were on June 11, it's changed. It's now in Taurus. So make of that what you will, but like many of tonight's stories, this notion of twins or not being a twin is going to come and go. So I've already broken the idea that June 11 was the constellation we're in for Gemini. But on top of it, Castor and Pollux, those two bright stars up there, they're not related to one another either. They're dozens of light years away from one another. I think it's Castor that has 6 stars in its group. So one of those bright dots is actually 6 stars, and the other is an F0 type 3 giant star. It's actually the closest star of that classification to the Earth. So there's really 7 stars there, and the 2 aren't related at all. So like a lot of our stories, we're going to blow up the notion of what is a double. The Kepler Space Telescope, which was an exoplanet hunting craft that went and looked for planets orbiting other stars, which we call exoplanets. They did a series of posters that were just kind of fun, that were based on actual objects that were found. And Kepler 16b is a real planet that has 2 suns, and they made this poster for it. So that's a real binary star, unlike Castor and Pollux, which are twins, but they're not even related in the sky. There are stars that orbit one another. They were born that way, they grew up that way, and sometimes they die that way. And here's a beautiful view of what it might look like on the surface of a moon around that gas giant that orbits these 2 stars. So you could visit the moon, maybe put on your spacesuit and enjoy a Tatooine-like view, which would be fun. But now I'd like to introduce our guest. Devin, you're going to talk a little bit about double stars, sort of, but they're in a really different environment. You work on the Galactic Center at UCLA. So I'm very excited to hear what you have. So everybody, welcome Devin tonight, Dr. Tu, and take it away. Let's talk about these stars at the Galactic Center and what you do.
Right. Well, thank you so much for that introduction. It was really an honor to be here for All Space Considered. Griffith Observatory is a very soft spot in my heart, especially ever since I came to UCLA to study astronomy. And so tonight, as alluded to, I'll be talking about binary stars, but more so actually, I should say, missing binary stars near this black hole at the center of our Milky Way galaxy. And again, just introducing myself again, I'm Devin Chu. I'm currently a postdoc at UCLA working with the UCLA Galactic Center group. And so I'll be presenting a lot of the work that we've been doing as a collaboration. So but first, I'll talk a little bit about myself and my introduction. So for some history, I grew up in Hilo, Hawaii. So on the left here is a little map of the state of Hawaii, and I circled the location of Hilo. It is located on Hawaii Island, which is the largest of the Hawaiian Islands. So it's also called the Big Island. Sometimes I've heard people think Honolulu and Oahu, that's the Big Island. Like, no. Hawaii Island is the Big Island when it's being referred to that way. So for some other background, I'm a 5th generation Hawaii Island boy. My ancestors came from Japan during the 1800s, and they came to Hawaii Island to work on the sugar plantations. So my family has called Hilo home ever since. This photo of the right here is a view of Hilo Bay with the prominent volcano of Mauna Kea in the background. Mauna Kea is one of the most famous sites for astronomical research. Hopefully in this photo you can also see the lush greenery. Hilo gets an average of 142 inches of rain every year, which is about 10 times that of Los Angeles. So I would say I got used to some rainy weather growing up there. Now I really consider Hilo definitely sort of a small town Hawaii feel. In fact, Hilo's entire population of 42,000 can fit comfortably inside Dodger Stadium with lots of room to spare. So I remember growing up, watching Dodger games, cheering them from afar, and still being amazed that, if we all in Hilo wanted to go watch a Dodger game together, we could. We all could have gone to the Dodger game today and get a Clayton Kershaw bobblehead, but it's a little harder to transport all of us over there. But I just thought it just kind of blew my mind that our entire town could fit in like Dodger Stadium, which was something very interesting to me. So growing up in Hilo, I became very interested in astronomy at a young age. It all started going to the Hilo Public Library. My mom and we went to the library. We checked out a book called Our Solar System. When I saw the photos of the planets, the comets, asteroids, I was absolutely amazed. I was blown away. That got me hooked on astronomy. So shout out to public libraries everywhere. So as I grew up, I continued to attend science camps and work on science fair projects. And I was really fortunate to have the opportunity to work with scientists at the nearby astronomical observatories on different science fair projects. And these experiences really fostered my interest in science and inspired me to study astronomy. I viewed astronomy as an opportunity for local kids such as myself to have a job in Hilo. And I also viewed it as a way to explore the universe around it. So some of my colleagues that are Native Hawaiian, they view astronomy as a way of carrying on the navigational spirit of the Native Hawaiian people, and that's very much how I view myself, a way to explore and navigate the universe that we have yet to really fully understand. So while I was growing up, I wasn't aware at the time of some of this incredible astronomy that was happening just up the slopes of Mauna Kea, being done by scientists at UCLA. The UCLA Galactic Center group was using the Keck Observatory to study the very center of the Milky Way galaxy. So every summer, they pointed their telescopes to the same spot in the sky, trying to see what they could learn about this really intriguing region. And so we fast forward to today, and I'm now actually a part of the UCLA Galactic Center group. So here we are standing in front of the Keck Observatory at Mauna Kea, this time during the day, so you can see the nice bright sunlight and blue skies. And when I came to UCLA as a graduate student and I conducted my own research with the group, it really was a very surreal experience being able to return home and conduct research there. It really came full circle to me, I would say. And so I really want to emphasize that what I would present today is really the work that was made possible by our entire group. It's not all something that I've done by myself. It's really building upon the work that our entire group has worked on. So I'll begin by introducing our galaxy. So here's the top-down view of the Milky Way. We are located here at the orange circle, and the Milky Way Galactic Center is circled in yellow over there. So as you can see, our solar system is very much in the suburbs of the galaxy. We are far away from the incredibly dense stars that you can kind of see in the central region of the bar of the galaxy. Tons of stars are there. Where we are, not nearly as much. And so to get all the way to the Milky Way Galactic Center, you got to travel about 26,000 light years away. Again, it sounds pretty far, but then again, if we're interested in other centers of galaxies, this is the closest one we got. That's the closest one to get to. So it presents a great opportunity to study centers of galaxies by looking at our very own. So this here is a little video that's been made by the UC Galactic Center group traveling toward the very center of our galaxy. So after this little introductory slide here, we see here the position of famous constellations. So the center of the galaxy is in the southern part of the sky. So as we travel closer to the center, I really want to begin to emphasize that you see huge amounts of dust, the kind of dark spots there. So in order to peer through these dusts, we need to use infrared light wavelengths. So this particular image right here in red, this is taken by the Spitzer Space Telescope, which looks at infrared light. Again, we keep zooming. I just really want to emphasize, look how many stars there are. Look how crowded and dense it is. And we're going to keep zooming until finally we are here at our final zoom, where we're looking at the very heart here. And I want to say over here, over the last few decades, the UCLA Galactic Center group has tracked the motions of these stars in this region. And what's really interesting is that these stars seem to orbit around a point in space denoted by that white star right there. And interestingly, it doesn't really emit a lot of light on its own, yet if we use the laws of gravity, we can calculate that these stars must be orbiting something that is 4 million times the mass of our sun. So we can really conclude that these stars orbit a supermassive black hole. So just on the left here is an image of Sagittarius A star, or the supermassive black hole at the center of our galaxy, taken by the Event Horizon Telescope. And I just drew an arrow there. It's right in the smack of the middle where all these orbits of these stars are. So again, just like a really interesting that, again, using these orbits and motions of stars and laws of gravity, we can conclude that this black hole is 4 million times out of our sun. And so sometimes I personally find it hard to imagine when someone says, oh, that's 4 million times more. It's kind of hard to think about those type of big numbers. So especially when it comes to like mass. So the way I like to think about it is if you take my mass and you multiply that by 4 million, you get the Empire State Building. So suffice to say, is a very big difference between our sun and the central supermassive black hole. And so the discovery of this central supermassive black hole led to the 2020 Nobel Prize in Physics for the UCLA professor Andrea Ghez, who is head of the UCLA Galactic Center group. And this really, I think, speaks to the importance of this finding. So on the right is a photo of me with Professor Ghez at my PhD graduation. It's really been an honor to work with Professor Ghez during my time at UCLA. And we were all working remotely at the time because of the pandemic when the Nobel Prize announcement took place. So we had to delay our in-person celebrations for a while, but it was we all had a great time celebrating her as a monumental achievement. So I talked a little bit about the black hole and the galactic center, so I want to return now to those stars that we saw orbiting that central supermassive black hole. What's really interesting about these stars is that they're very different compared to the star that we are closest to and most familiar with, which is our sun. So again, these stars at the galactic center, they are incredibly massive, hot, and young. And so the right figure on the right here just kind of shows some differences of what our sun, looks like compared to these galactic center stars. So you can see here the sun looks kind of orange and small, but if you go to the right there, the galactic center stars are like burned blue and they're much larger. And so when I say again these stars are massive, I mean that they are 10 times as massive, more massive than our sun. When I say hotter, they're 5 times hotter. So that's why they burn blue and not like orange or yellow. And when I say young, they're like 6 million years old versus about 5 billion years old. And again, thinking about the 14.8 billion year old universe, 6 million years is pretty young. So again, that's why we can classify these stars with these particular descriptors. And so what's interesting about massive stars is that our understanding is that most of these stars come in pairs. And so in astronomy, a pair of stars is called a binary star system. And so studies of binary stars, especially in our solar neighborhood, seem to show that about 70% of massive stars come in binary star systems. We think this has to do with the way massive stars form and the surrounding environments that they are in, such as in like these really dense star clusters. So basically, as astronomers, we're trained to think that if we find a massive star, it's very likely and highly probable that it's part of a binary star system. So this raises an interesting question, saying, okay, well, are the stars at the galactic center so close to the supermassive black hole? Are they also in binary systems? And one could think, again, since they're massive stars, they probably are. So one of the things we want to do is see if that's actually the case. And so unfortunately, finding binary stars at the galactic center is a non-trivial process and takes time. We can't, unfortunately, take a single snapshot of some stars and say, yeah, yes, that's a binary star system. And that's because these stars are so far away. Again, they're like 26,000 light years away. You just can't resolve 2 individual stars when they're that far. One way I like to think about it is if you see a car driving like from the very far distance and you see the headlights, right? It looks like one single headlight. But once the car comes closer, you can then resolve the 2 headlights. Like maybe there's some fog lamps as well. So that's sort of what we're dealing with here. These stars are so far away, we can't just take a single snapshot and say, oh yeah, those are 2 stars and not 1. So that's one of the challenges that we're dealing with. And so what I'll be talking about over the next few slides is how we use particular tools to make this experiment of looking for binary stars at our galactic center work. So the first tool I want to talk about here is this thing called adaptive optics. It is a very crucial tool for what we're doing here, and essentially what we're trying to do is correct for the Earth's atmosphere. So our own Earth atmosphere, it distorts starlight. It's the reason why we have the song Twinkle, Twinkle, Little Star. It's a nice song, it's pretty, but it is really not that helpful for astronomy. It's very detrimental. The atmosphere, again, the atmosphere is important too. Without the atmosphere, we would not be here. But for looking at astronomical sources, it gets in the way sometimes. And a way I like to think about this is like if we look at a running riverbed, like for instance, a photo here on the right, if you try to look at the bottom of a riverbed in a flowing stream, the current of the water distorts the riverbed, so it's hard to see sometimes individual pebbles and stones at the bottom. That's essentially what our atmosphere is doing. So I just back up here, going to this figure on the left. Without adaptive optics, when we're looking at the very central region close to where the supermassive black hole, things are kind of smudged out, blurred together. Now, when we turn adaptive optics on, what we're doing is we're actively correcting for the Earth's turbulent atmosphere. So you can see here this video should now be playing, and it shows what adaptive optics does. It now makes us actually resolve individual stars. And so when I showed these photos of Keck Observatory with these lasers pointing at the stars at the Galactic Center, these lasers are actually part of our adaptive optics system. So what's pretty cool is if you like lasers, as astronomers, we definitely use them to do some really cool science. So that's what these lasers are doing. They're part of our adaptive optics system. And so what this adaptive optics system does is it essentially allows us to correct for the Earth's atmosphere and allows us to essentially you could say go to a calm and quiet part of the stream. So like on the bottom right where there's not a lot of water flowing, you can see clearly pebbles and stones. That's essentially what adaptive optics is doing. And I want to emphasize it is absolutely crucial for what we're doing, because without it, we have a really difficult time identifying individual sources at the Galactic Center. Everything blends together. The other tool I really want to emphasize here is the spectrum of light. So as an observer at a telescope, we see light emitted from the stellar source, and what we want to do is then split this light up into its individual wavelengths. So this is very much how like a prism turns white light into a rainbow. What we get is this rainbow spectrum of light, and this spectrum of light is very important, which I'll be talking about the next slide here. Because what we do is we then use this spectrum of light to see if we can use that spectrum of light to see if we can detect stars orbiting around each other. So this video should show how this technique is used. So what we do is we look at the star spectrum over time. Like this is very important. Over time, we have to keep coming back and looking at the star spectrum. And so what we're going to keep doing is looking at that little rainbow spot there that's circled in yellow. And over time, we want to see if this spectrum changes. So if in fact it is a binary star system and they're orbiting around each other, they're essentially kind of orbiting around, wobbling around the center of mass, and we can actually detect that shift. What we're doing is we're looking at those, like if you can see those really dark lines in the spectrum, those are features of the star. We can see them drift back and forth, and if it's periodic, that's a sign that in fact it's a binary star system orbiting a center of mass. And that's what I want to say as a side note. This same method is used to find planets around other stars. So as a planet orbits the star will also wobble. And at these telescopes, we can then detect this very faint wobble to confirm the existence of extrasolar planets. So very related technique for those that are interested in extrasolar planets. Okay, so we want to collect all this spectrum, stellar spectrum, spectra, I should say, and get all this data. And so that's what I'll be talking a little bit about here. So again, to emphasize, we need to take a lot of spectra over time to see if we can detect this periodic signal. And so we just need a lot of data, right? If you want to collect, really detect something like that, you want to make sure you keep coming back to see if we can be sensitive to these changes. And so there's a lot of data involved. So really for the last decade, we've been looking at these stellar spectra. And so I'll talk a little bit more about what that process is like. So unlike growing up as a kid, I don't look through an eyepiece of a telescope. Rather, I'm using a lot of computers. So the photo on the left is of me actually on Hawaii Island in Waimea, which is where the headquarters of the Keck Observatory are. And so yeah, we need to use computers because we need to adjust these huge telescopes that can get a sense from those domes to very fine precision. So you need computers to do that, and you also need the computers to process the incredibly complex data that comes in, all the electronics that are involved. So again, it's not the classic looking through an eyepiece and seeing that spectrum that way. It's all through these computers. What's also interesting is that while it's great to come back to Hawaii, we also don't necessarily have to. We can actually control the telescopes from UCLA. So that top right photo is of Professor Andrea Guez. She's on the far left, and then some members of our team actually controlling the telescopes from UCLA. So if needed, we can be at UCLA and drive the telescopes from there. And one of the things I'll say that is about so this photo on the bottom right, this is again going back to Hawaii. This here actually shows a photo of the Keck Observatory headquarters. It is morning twilight, so the sun is just about to rise up, and that is a Venus there. And I just want to say, like, right, this is the start of most people's days, but really I was heading off to bed. So that is the life of an observational astronomer. When the sun comes up, it means, all right, it's time for me to go to bed. Okay, so again, we looked at over a decade of data looking for these spectroscopic binary stars around the supermassive black hole. And again, this slide here will show a little schematic of kind of what we were expecting. So based on the sample of stars that I was focused on, and our knowledge that about 70% of massive stars should come in binary stars or in pairs, we would predict to find a majority of these stars to be in pairs. You know, it wouldn't be surprising to find a few single stars, but the main point I want to emphasize is that most of them should be in binary stars. But that's not what we found. We didn't find any. of the entire sample that my project focused on, we didn't find a single binary star system. And this is interesting, right? Again, one would expect we would find most of them be binary stars, or hey, maybe perhaps a few binary stars, or maybe at least one binary star system. But we didn't find any of them. We didn't detect a single one. So which is interesting. But I will say, that being said, is this result surprising? And I actually would say yes and no. So to drive again this point, again, this is interesting and surprising because, again, we expect most massive stars to come in pairs. So therefore, if we extrapolate that to the Galactic Center, we would expect the same thing. But then I would also say that's maybe not, the fact that we don't find any binary stars is not that surprising because the environment around the supermassive black hole is very different compared to our solar neighborhood. Then coming back to that map of the Milky Way galaxy and focusing again on our regions, if we look at our solar neighborhood and our Galactic Center, they're very different. The density of stars at the Galactic Center is much higher at the Galactic Center than in our solar neighborhood. And so again, then it's so then with that said, why would we should we expect binary stars to behave the same way? And a lot of the studies, I should say, where we think a lot of massive stars come in binary star systems, these studies focused on areas that were similar to our solar neighborhood, out in the galactic suburbs, not in the heart of downtown. So that's one reason why maybe it's not that surprising that we don't find that many binary stars so close to the supermassive black hole. I like to think of it like this, right? Imagine comparing traffic patterns at different locations. So our solar neighborhood is like Hilo, right? It's not very dense. There are a lot fewer stars where we are. And the Galactic Center is like downtown LA, very dense and crowded. So if I were to come from Hilo and say, oh yeah, I know what traffic is, and then plop onto like downtown Los Angeles at 5 p.m., I would be in for a very rude awakening. But again, because the environments are very different. So that's just a clear example of how environments have a major impact on different processes, and in this case, traffic. And I also want to stress too as well that another reason why maybe not finding any binary stars so close to the supermassive black hole is not surprising is because the supermassive black hole itself is very hostile to binary stars. The gravitational force from the supermassive black hole is not friendly to these systems, and I'll explain more about why that is over these next few slides. So one thing that the supermassive black hole is that it can cause binary stars to merge. So let's say we have a binary star system with two sun-like stars that are orbiting around each other. The black hole actually influences this binary star orbit and causes these stars to merge. So what happens is the result is that you have these, they merge into a single star. And the product of this merger is that a single star can actually look very much like a very single hot massive star like the Galactic Center stars that we see today. Additionally, the supermassive black hole can also rip apart binary star systems. So let's say we have a binary star system of two massive stars that pass close to the supermassive black hole. The black hole's strong gravitational force tears apart the binary star system. One star is ejected from the region and is flown out at incredibly high speeds, again at thousands of kilometers per second. Very, very fast. These are some of the fastest stars in our galaxy. They're ejected from this region. What is really cool is that we actually observe hypervelocity stars in our galaxy, which could suggest that they come via this mechanism from the Galactic Center. And again, the other star of the system remains orbiting the black hole as the Galactic Center star that we see today. So this here is just some of my concluding slides, just to talk about some of the key points here again. I just want to say again that massive stars orbit the supermassive black hole at the very center of our Milky Way galaxy. And what's interesting that we do not see any of these binaries, we do not see any binary star systems amongst these massive stars so close to the supermassive black hole, even though studies suggest that most massive stars come in binary star systems. And perhaps the supermassive black hole itself may play a role in causing these binary star systems to merge or disrupt, and may explain why there's a lack of binary stars so close to this black hole. So I want to say thank you so much for this time, and mahalo nui loa. It's a pleasure. And thank you again for this opportunity to speak to you all tonight.
Wow, well, I know we have some time for some questions. Let me see if there are any within our audience here. Anyone in our audience have a question? Yeah, down here in the front.
Yes. Oh, okay.
Yeah.
Are you going to continue looking at other stars at the Galactic Center to see if there are binaries in there?
Yeah.
Or
And I'll repeat the question for our YouTube audience out there. The question was if Devin's going to continue to look at other stars to try and find binaries near the Galactic Center.
Yeah, the answer is absolutely yes. So I would say one of the things that our group is primarily interested in is those orbits of the stars so close. And so naturally, to get really good orbits, we want to keep looking at these stars over time. And then I would say one of the nice benefits of this key science project is the work that I'm focused on is looking for binary star systems. So a lot of my work established the way that we can look for binary stars amongst these particular stars. And then what's great is we can just continue to monitor them. And essentially, the longer we look at them and not find anything, that just further supports what we've been finding. Or we could even be pleasantly surprised. I would say pleasantly surprised and find one. But the main answer is yes, we're going to keep looking for binary stars because we think it's a great place to look for them.
Excellent. Did I see a question up over here?
Up there.
Over here, yeah.
Do you plan to look at like other galactic centers of different galaxies and compare that to ours?
The question was if he's going to look at other galactic centers of other galaxies and compare them to our galaxy.
That's a great question. So personally, we're really interested in our own galactic center. And the one reason is, again, it is the closest one to us. So we benefit from actually getting to see individual stars at our own galactic center. The moment you go to another nearby galaxy, the closest one, it becomes incredibly challenging to even resolve individual stars. Again, it's a challenge in our own galaxy, let alone in other galaxies. That being said, with the advent of some advanced, the new, hopefully large-scale telescopes, I believe you can start to play that game. I think it becomes possible. But right now, it's just too hard because those galaxies are too far away. But again, we would be very interested because maybe our galactic center is different from other galaxies. So I think expanding that search to other galaxies is a great question.
Here.
Can you tell us why there's a profusion of very massive, very hot stars at the center of the galaxy?
Yeah. The question was, why are there so many hot, massive, young stars in the center of a galaxy? Hot young stars, as the saying at All Space Considered goes.
Yeah, that is a great question. So that's one of the big science questions that we are interested in at the Galactic Center group. Right now, the challenge was, again, the supermassive black hole. It is not only hostile to binary stars, it is hostile to star formation. So it's really hard to form stars so close to supermassive black hole because the way a star forms, we got to take a gas cloud and really collapse and condense it. You throw a supermassive black hole there, start shearing things apart. And so the fact that we found such massive stars at the center of the galaxy is a huge question that a lot of us are still trying to figure out. So the way I kind of look at it is, I'm dealing with the fact that they're there, and that's interesting. But to then ask the question of how they first got there is a really interesting question in which I don't feel that qualified to answer. But a lot of it, you had to start, the main thing we had to think about is we have to rethink how star formation works. Because the traditional classic way doesn't work at the Galactic Center. So we have to invoke special processes, special conditions, special circumstances in order to even get stars that massive so close. And I should say maybe one thing is it's not that surprising to find old stars at the Galactic Center because you can form things out and bring them in. But the challenge is, again, these stars are young. They don't have a lot of time to travel from somewhere else to get there. And so the fact that we see them there means they probably formed there. But then how they formed there, again, that's a very interesting question. Traditional star formation cannot explain that.
There's another question here. Yeah.
Question surrounding the observation of the black hole that is close to the Galactic Center. It's a naive question. Do all galaxies surround and generate out of a black hole?
So the question was, do all galaxies have a central black hole to them, essentially?
Yeah, the answer is it looks like pretty much most galaxies have a central supermassive black hole, which is really interesting and then speaks to how important that central supermassive black hole is for the formation of galaxies throughout our universe. One of the cool things about our galaxy and our galaxy's supermassive black hole is we have really the strongest evidence that it is a supermassive black hole because of the orbits of these stars at the galactic center.
Up in the corner, we have a couple of questions there, and then we'll turn to our YouTube audience for a couple of questions. So in the way back in the corner.
We're in the middle of this AI craziness. Do you have some positive usage for AI for your science and for your work?
Yeah. The question was, can AI be of use in your science in a positive way?
Yeah, I would say for my particular science case, a lot of it is still is really helpful for like me as a human to look at it. But AI is it's definitely a huge part of astronomy. As you can imagine, astronomers, we take a ton of pictures, and with some of these new telescopes coming online, they're going to be taking more and more and more pictures of the night sky all the time. And what AI can really help out is with helping classify things like, is this type of galaxy? Is it another type of galaxy? Is this a type of star? Is this another type of star? Right, we're going to be dealing with, terabytes of data. And so AI can help essentially with that work of helping sort things and identify things. That's where I think AI is really helpful in doing those particular tasks. It's already essentially being done. But yeah, that's a huge field in astronomy right now, is how we can use AI and machine learning for astronomical data.
And then the other question, yeah.
I hesitate because it's a very naive question. Very naive. But you were talking about how you extrapolate what could happen based on sort of laws of physics here and things like gravity. How do we know gravity is the same there than here? And how can we make those predictions with accuracy?
Yeah, so the question was, how do we know that essentially the laws of physics, things like gravity, are the same at the Galactic Center as they are here?
I think it's a great question, not a naive question at all, because we actually are asking that ourselves at the Galactic Center group, right? We shouldn't necessarily assume, we could go into it thinking, should gravity be the same here on Earth as at the Galactic Center near a supermassive black hole? So I unfortunately don't have any slides or material, but that's one of the big things that our group has been doing. So we want to test to see if we can see if Einstein's theory of relativity, general relativity, works at the Galactic Center. And some of the results that we have are right now it shows that it agrees. Another thing that we've done as well is, if anyone's familiar with the fine structure constant, it's a constant I think has a lot to do with the way atoms and different energy transformations work. We can test if that holds true next to supermassive black hole. And we've done actually some of these tests, and right now things seem to be holding up. But yeah, again, I want to really want to reiterate that that's not a naive question. It's something that we want to ask ourselves, because we shouldn't assume that. It is a good thing that we can experimentally test, and that's one thing. That's what we've been doing.
Excellent. Now, a couple questions from our YouTube stream. It looks like R1, I'm sorry if I'm pronouncing your name wrong, wants to know, are there any telltale signs if two stars merge? Does it leave behind any gas or anything we can see?
Really great question. So what happens with a stellar merger is a really interesting question that a lot of people are thinking about, but we think perhaps maybe shortly after the collision happens, you'll get the atmospheres of the stars kind of flowing out. So you might get this kind of puffy envelope feature. And so you might have the cores of the stars still radiating inside, but this kind of puffy envelope as that big collision took place. We think we actually see those types of objects there, which again could lend support for this merger hypothesis at the Galactic Center. Again, there's a lot of work to be done on that front, but we think that's kind of a very general, very high-level answer to that question.
Mm-hmm. And then one other question was, has anybody traced back one of those hypervelocity stars to the Galactic Center? Are we sure that's where they come from?
Yeah, that's another great question. So that is a very difficult thing to do, more so because, again, we're working with 3D velocities, but there was a famous hypervelocity star discovered a couple years ago, and one of the big key results is they were able to trace that back to the Galactic Center. But yeah, it's a very difficult process, but that's, whenever we find one, that's one of the big questions, can we trace that back? And the other thing I should say is because you could also get these from supernova explosions outside of the Galactic Center, so they don't necessarily have to come only from the Galactic Center. So the key is, right, how can we figure out where this hypervelocity star comes from is about tracing back that star's origin. Again, it's a very non-trivial thing. You can imagine trying to figure out a 3D, like where does something come from, but you only get a good 2D picture of the sky.
Well, once again, I'd like to have our audience thank Dr. Devin Chu for us. Wonderful time hearing about stars. And then I guess we can have you take a seat in our audience, and we'll have our panel scoot on down.
Oh, wait.
Yeah, come on down this way.
Oh, okay. Guess we can all move.
We'll all scoot down. Okay. Turn my power back on, and now it is time for our Sky Report with Patrick. So what has been up in the sky in June, and what's in store for us?
All right, so here's our mid-month June Sky Report from the relative safety of the Earth and from the suburbs of a region of the Milky Way. In this picture, I took this just a few days ago, and that bright object there is the planet Venus, which has been in our skies for several months now. And if you have not had an opportunity to see it, or if you've already seen the object and don't know what it is, that's what that object is. Second planet closest to the sun. So I know it's been cloudy here for we've had a lot of June gloom, so it might not be as opportune to see it. So anyway, I've been able to track just by taking photographs with my cell phone the movement of Venus from last month. So we'll go to the next picture here. So as the sky darkens, you can see that Venus shines brilliantly over in the west, and it's amongst some stars that Dr. Wrightsaw had mentioned, and those stars represent the constellation Gemini, the twins.
But the sun's not there.
Yeah, Venus is there.
Venus is there.
So that was on May 16th, and you can see the bright stars. Castor and Pollux represents the head of the twins. Now, we're going to fast forward just to a few days ago, because I was out in the high desert, and I took this picture just about an hour after sunset. And you can see Castor and Pollux, and I've indicated with a dot, kind of an arrow with a dotted line, where Venus was and where it is just a few days ago. It's moved quite a distance. In fact, it's moved an angular distance of 28 degrees from its May 16th position. So it does kind of drift very quickly through the sky. Now, what constellation is it in? Well, it's really hard to see because it's moved into a faint constellation, which is Cancer the Crab. And I've drawn the lines there, as you can see, just barely. The constellation itself, it's made up of stars that you can see, say, from suburban or even rural areas, which is much easier to see. So that's where Venus is just as a few days ago. And not far from Venus is the planet Mars. And I went too quickly. There's Mars. And Mars is not as bright. It is quite far away right now. Right now it's 196 million miles away from Earth. So it's roughly about as bright as the star Castor. So if you just want a comparison there. We'll go to the next event, and hopefully this will work. There we go. So we're going to just jump ahead to June 21st. So at 9 p.m., the moon joins Venus and Mars in the evening sky, forming a beautiful trio. In fact, the moon is just about 3.5 days old, so it's a slender, waxing crescent moon. And we'll take a look at this configuration. Very beautiful and definitely not to be missed. So if you mark your calendars, go out on the evening of the 21st and look for the crescent moon, Venus and Mars, and they form a beautiful right-angled triangle in the sky. Now, June 21st is an interesting day astronomically because it is the first day of summer. And that day is marked by the summer solstice, which occurs at precisely 7:58 a.m. in the morning, Pacific Daylight Time. And during this moment, the sun reaches its farthest northern point along its annual path, or ecliptic, which is represented by that curved red line in the diagram there. And that's, of course, in the northern hemisphere. So in Los Angeles, local noon occurs at 12:55 p.m. PDT, and this is when the sun reaches its maximum altitude above due south of 79 degrees. So that's the highest it will reach from Los Angeles. From other locations, it's different. So this also signifies the highest noontime position for the whole year. And what about these seasons? Well, we often say, okay, well, it's summer solstice, and that actually summer begins in the northern hemisphere at 7:58 a.m. But actually, conversely, in the southern hemisphere, it's the start of winter because the seasons are reversed. So that's an interesting thought for our neighbors there who have experienced a long summer and are now experiencing the first day of winter on the 21st. Now a quick look at our evening sky. So just for you stargazers out there, we're looking, as we look towards the south, we can see the spring constellations of Leo the Lion and Virgo the Maiden, which are gracefully positioned to the southwest. And then just to the due south, we see the summer constellations, Libra the Scales, Scorpius the Scorpion, and Sagittarius the Archer, which is just about rising in the southeast. And we're going to highlight one of these constellations, and that is Scorpius the Scorpion. Now, during the June evening, Scorpius is seen rising in the south-southeast. And we'll go to this picture here. Here it is. This picture was taken by Anthony Perkins, our telescope demonstrator, showing the Scorpion, which has just appeared over the horizon. Its brightest star is Antares, a reddish star, almost the same color as Mars, and is also known as the ancients, the rival of Mars. We're going to highlight something else in Scorpius. If you follow the curve of the Scorpion's body, the head is at the top there, marked by that triangular arrangement of stars. In that circle there are two stars, and in the theme of double stars, if we look very closely at it, you can indeed see two stars almost the same brightness, but very close together. And that double arrangement of stars is a binary system known as Mu Scorpii. And it comprises of stars roughly about third magnitude. So when Scorpius rises higher in the sky, if you can see those stars and separate them, they're roughly about 1/5 of the moon's diameter. That's a good test for your eyesight. I don't think I can see that, but it's actually very close.
Time for new glasses.
Yes, indeed, yeah. Well, actually, for you younger members of the audience, you shouldn't have any trouble discerning this pair of stars here. So this is a close telescopic look at it. There's Mu1 on the right, which is the brighter of the pair, and Mu2, the fainter. And there's, notice the bluish color. These are bluish giant stars, fairly close together, located about 500 light years from Earth. So interesting that you can actually have this visible, and you can actually see it if you have very good eyesight, except for myself, excepted.
Mm-hmm.
So
we'll get you a pair of binoculars.
Yeah, well, no, that's what I was going to say, that binoculars will definitely show these very easily. So do take a look in that region of the sky, locate Scorpius, and look for Mu Scorpii. All right, so we talked about planets in the evening. Mars and Venus are in the evening sky, but what about the other planets? Well, in the morning sky, if you get up really early, you can get a glimpse of the planet Saturn, which is in the faint constellation of Aquarius. And the other planet, the largest planet in our solar system, Jupiter, this brilliant planet is in the east, and you can see that rising around about 4 a.m. So you can get a glimpse of these two planets, which have been hiding out in the morning. Do go out and take a look at these planets. They will be migrating into the evening sky later on in the next few months. All right, so a quick look at our moon phases. We had, let's see, we had full moon on the 3rd, last quarter on the 10th, and new moon on the 17th, and then the first quarter on the 26th. So that's what we have to look for this month.
Well, fantastic. Thank you so much for that, Patrick.
Sure.
Well, this is our short break video, so if folks in our audience want to stand up, stretch your legs. Those at home, you have a couple of minutes, get a beverage, or just enjoy the beautiful music and the beautiful images. Okay, well, normally now we would have a section, a history of seeing double, but like I said, we're not able to bring you this tonight because Chris Butler, who was going to be with us, was not feeling well. So let me skip ahead here. I will try and do a little bit of magic on the stage with a little nubbin. That's not a mouse. Don't laugh at me too much, everybody. There we go, and now I can, I hope, forward us. Let's see what this does. That doesn't work. Let's try. It is good TV, everybody. Watching Rights will struggle. Here we go. There it goes. So we're skipping. All right, well, let's go to some simulated images of double stars. And Vanessa can tell us a little bit about whether we got this right or not and how it looks. So let's take a look here. This is 61 Cygni, and this is a 12 arc-minute field. By the way, the moon is about 30 arc minutes across. So this is about a third of the moon's diameter in this field of view. Can we see these here from Griffith Observatory?
Yes, you can. Yeah, we do have a couple of telescopes that are on the front lawn every day that we're open. And they're 11-inch telescopes, so you can actually see them from all of those. But also upstairs we have our 12-inch size. And Cygnus is going to be up this summer, so if you want to come up here and take a look at some double stars, we'll be showing them throughout the summer.
Yeah, we don't take requests necessarily, but you know, if you let us know early enough, maybe during the night we can switch to one. Here's another example, and two more.
Yeah, this one is one of my favorites. It's the double. I think it's two double stars for one, 2 for 1. So you have two that are really close to each other. You can almost not even really separate them, but that's actually 4 stars there total, and you can actually see both of those through the telescopes here.
Very cool.
I really like this one.
And then there's Castor.
Castor, yeah. I specifically asked for this one because we did talk about the twins, and you can't go and talk about the twins and not talk about Castor being a kind of a triple double. So it's 3 double stars kind of, and they're orbiting around each other. They have a really complex orbit. It's super cool. So.
Yeah, very, very cool.
But they are really hard to resolve. They're very close to each other.
And what about Acrab, or crab? How do you say it? Crab?
Yeah, you can also call it Beta Scorpii. Yeah, so this one is also really close to each other. They're very close. But this is also a 6-star system.
Wow.
So another cool one that you can see, you can't see all 6 stars, but you can see 2 of them. And just imagine all the other ones kind of orbiting around. It's kind of fun.
So this is really common for stars to have companions. Our sun, it's a little bit unusual that we're a single star, actually.
Yeah.
Now, what about Alberio? This is a star name I've heard a lot. What's great about this one?
Alberio, I said the other one was my favorite, but this one is a really good one for showing the different temperatures of stars. You can actually see 2 different temperatures in these stars right now. So the blue one is hotter than the yellow one, even though the yellow one is much bigger. But also, again, this is another system of stars. It's not actually just 2 stars. I believe there's like 4 of them here. There's a total, if I remember correctly.
Yeah, exactly. And those, it's great to be able to see different colors through a telescope with stars. A lot of folks, you can kind of notice in the night sky they are, and when you see them through a telescope, it brings a different perception to the whole thing.
Definitely. So. Yeah, and this one, if you look at it in the sky just with your eyes, it looks like a single star, same with most of those other ones. But then you get a telescope or binoculars out, and then you see 2. It's pretty, it's cool. Fun.
Well, and now you're going to tell us about something that's also kind of a binary of sorts, but not stars.
Definitely not stars.
Yeah, definitely not stars.
Yeah.
So you're going to talk about some galaxies and some black holes at the centers of galaxies, and will they merge? So
yeah.
Will they?
So that's a good question. So this, what I intended for this title is to be more like a game show, kind of like, will they merge? So say that in your head when you see it. So yeah, these 3 galaxies are merging here, and as we talked about earlier, there were probably supermassive black holes at the center of these galaxies, as most galaxies have. These ones are actually, this is kind of just a fun fact, they're like 50,000 light years away from each other, which is really, really close, because the closest galaxy to us, major galaxy, is about 2.5 million light years away. So these are really, really close to each other. They are merging. But I want to talk about the black holes at the center of them. So before I go into, supermassive black holes, there are, just give you some background on how black holes are classified. So there's 3 major types. There are stellar mass black holes. This is classification based on their mass. There's other factors too, but stellar mass black holes, there's intermediate mass black holes, and supermassive black holes. So the stellar mass black holes we think are formed from supernovae. So you've probably heard that. Star dies and it leaves behind a remnant, and the remnant is a black hole sometimes, if the star is massive enough. And there's these are actually the types of black holes that we've seen merge through LIGO. So those of you here, how many of you are familiar with LIGO and gravitational waves? Anybody? Got a few hands. Good, good, good. So these are the actual some of the as you can see up there, some of the black hole mergers that we've seen, and they are lower mass black holes, so the stellar mass ones. So even when they merge, they just turn into bigger stellar mass black holes, so around still under 100 solar masses. So for those of you that aren't familiar with LIGO, I'll just go real quickly just about what it is. So this is LIGO. This is an instrument that can detect gravitational waves. So gravitational waves, basically what this is are just a bunch of lasers. So it's 2 really long lasers that stretch on for I think it's over a mile. It's really far out. And the lasers are really sensitive, and they can tell when space-time itself is shifting and moving around. So these are an artist's interpretation of what gravitational waves look like. And in these aren't black holes, they are neutron stars, but they're also supermassive compact objects that can merge and produce gravitational waves, which are, again, just things that we can observe, which are disturbances in space-time. So intermediate mass black holes, go over it. It's a whole mystery on its own. As you can see, this infographic has a question mark in it. So we don't actually know, haven't observed these directly.
I think a couple now.
We've actually observed them
really
directly.
recently.
Okay,
Yeah, I
good,
think there's been a
nice.
measurement of a couple, but
Okay, great, yeah.
I will have, but my memory's foggy on it. So next show, maybe we'll find out if
Yeah,
I'm
yeah,
right or
which
if I'm
ones.
making up things in my brain. I might be.
Yeah. But yeah, so they're not very common, even if we have seen them.
No, and
yeah.
they're super rare, and it was big news, I thought, when they
Yeah.
kind of found one, but maybe it'll go away. The detections don't always
Yeah.
stick around.
Yeah, when they get more information.
Yeah.
Maybe it's not. Yeah, so some people think that they might be from mergers of the smaller black holes, and then, or from population 3 stars, which were the really old first stars, which got more massive, were more massive and hotter than some of the stars that we have now, but that's a whole different story. But there's also supermassive black holes, which we think could also have formed through mergers of smaller black holes, intermediate, and also other supermassive black holes. You get two supermassive black holes, merge them together, you get an even bigger supermassive black hole. So the common theme here is merging. So they're formed through merging, but there is kind of a problem with this. But we have seen galaxies merge. This is the MICE NGC 4676, if you want to write that down. So these are, they probably do have supermassive black holes at the center, and as they merge, as galaxies merge, those black holes start off pretty far away from each other. So how do they get closer to each other is the question. So there's a big fancy word, it's dynamical friction, but what it is basically is stuff gets in the way of the whole system, and you can fling out stars. So these supermassive black holes will take these stars and use their gravitational energy and shoot them away, and the stars take the energy with them. They're traveling really, really quickly, and the system of the black holes loses that energy. So they start orbiting a little bit slower, they get a little bit closer to each other, and this happens over a long period of time. They get closer and closer and closer, and then until they get to the point where they don't have that many stars to fling away anymore. So how do you lose that energy? So one of the ways to do it is through gravitational waves. So gravitational waves do have energy, and as they are produced, the system loses energy and the black holes can get closer to each other. But that would take way longer than the time that the universe has been around. So that's not really a great explanation for all of them. But we have seen black holes that are relatively close to each other in galaxy mergers. So in this merger, we have X-ray images on the right side of two black holes that are supermassive black holes that got pretty close to each other. They're still really far away. They're about 700 parsecs apart. A parsec is about 3.26 light years. It's a really weird unit of measurement that astronomers use. It's because it's a little bit easier. The definition of it is that if you were to go really, really far away from the Earth, what is the distance that you would need to be away from the Earth to make the Earth the Earth's orbit a very specific size? It's about 27 times smaller. If you were to look up at the sky and see something that stretches across 27 times less than the size of Venus today, that is how far the Earth would have to be. It's a weird unit of measurement. It's 3.26 light years. That's all you need to know. So these galaxies that you see here, or these black holes, are about 700 parsecs away. So they are still really far. So they probably could still fling things out of the way and move closer together. But once you get to about 1 parsec apart, there's not much stuff to fling out. So scientists are kind of studying how do you get these galaxies to merge? How do you know, or these black holes to merge? What happens? What do you have to do? So there's a few explanations that could explain it. There's stars that kind of come through anyways. They get close enough because they're traveling fast throughout the galaxy, and they can get in the way, and then the black holes can lose some of their energy by flinging those way out of the galaxy. So that's what this is called. It's called the final parsec problem. And I chose this graphic because I really love the squiggles in there. I feel like it really brings together what's happening when the black holes are flinging away the stars. So you have this first step at the top, which is the galaxy collision, and then what we called the dynamical friction, which is stars getting flung away there on the bottom left. And then at the last bit, once you get really, really close to each other, you can get the final way and actually merge through gravitational waves on the right there. Yeah, we still don't know 100% how they all merge together. So there was one paper where they thought, what if all of that gas and dust and all of that stuff that's around these black holes, what if that is helping them come together? So how does the disk influence how the black holes react and how they merge? And this next thing you're going to see is a fun graph. So don't be alarmed. So the red means they don't merge, and the blue means they do merge. So they basically just made simulations of 80 different types of situations that could happen. So on the left side is like how big are the black holes compared to each other? Is one of them really big and one of them really small? So it's the ratio of the masses of them. So 0.1, you have one that's really small and one that's really big, and 1 to 1, you have them, they're both about the same size. So they did simulations of these 80, and 58 of them merged. So that is with very specific descriptions and parameters for the disk, but it can influence, and you can tell whether they will merge. Will they merge? Just based on how elongated their orbit is and the mass ratio, as long as the conditions that they presented in the paper are present in the system. So will they merge? Sometimes.
But what I find weird about this is it looks like objects which have a large mass ratio, so one is 10 times more massive than the other, merge when they have both small ellipticities and large ellipticities in their orbit. But if they're sort of in the middle, man, they're not going to merge.
Yeah.
It's a little weird.
Another thing they did too was they looked at how the eccentricities change over time, so how elongated the orbits are, and they noticed that they will generally go towards an equilibrium, so they'll go towards somewhere in the center there on the graph over time, and then from there merge. So yeah.
Very interesting. So, well, we'll have to see if LIGO starts picking these up in the future. I know, probably not in our lifetime, but still. Well, thank you so much. Well, Jared, are you ready to tell us about what's going on out there in space?
Yeah, we could start off by taking a quick trip to China because earlier, towards the beginning of this month, they had their Shenzhou 16 launch, so sending up another 3-person crew. I always like the little salute. Now, this 3-person crew was on its way to their space station, Tiangong-1, which already had the 3-person crew from Shenzhou 15 on board. And here's some great tracking footage of that first stage and booster SEP. And here's the separation of Shenzhou 16. And we'll see it move a little bit as the second stage begins to passivate itself. And here it is docking. And what was very interesting about this is that this is when we had the Axiom commercial mission on the International Space Station. So we had 11 people on the International Space Station, 6 on Tiangong-1. That meant that we had the most people in space ever with 17 folks. So we set a new record with that there. But of course, the Shenzhou 15 crew came back. Take a look. And that looks like that wasn't supposed to happen, but it is. Since the Shenzhou is very similar to the Russian Soyuz spacecraft, they have basically these braking rockets at the end, so the rockets will fire just before the capsule actually touches the ground. So it's not comfortable from the videos I've seen inside of Soyuz, so I imagine inside of a Shenzhou it's also not comfortable either. And of course, as I was talking about Axiom 2, they wrapped up their mission to come back home as well. A commercial venture. So these were not people. So these were people that paid to go and work at the space station, not to go up and goof off like most of the tourists that have bought their time to come on up. And I love this. We got Peggy Whitson, the commander, in the left seat, and I just really like Crew Dragon's user interface on there with all the touchscreens. I think that's astonishing and beautiful, and that's what Star Trek will probably look like at some point. But here you go. Here's our Dragon in the water after a successful re-entry and splashdown. And I like this little time lapse. Look at that guy climb up and then jump off the capsule. I want to do that, so probably didn't need to do that. But hey, if you're going to climb up a capsule, you might as well jump off of it into the water, right? So and, eventually they opened up the hatch and got the 4 astronauts out. So very happy for them. And we'll have to see what they do with their next Axiom 3 mission. And if you didn't hear, just a couple days before our previous All Space Considered, South Korea actually launched their own rocket for the 3rd time, their own commercial, their own private rocket. So North Korea decided to get in on the mix as well with it right there in that photo on the left. But it didn't make orbit. They had a problem right at stage separation for their first stage. And it just so happened that with the trajectory that they were taking, almost like it was a modified ballistic missile, it ended up splashing down and not destroying itself right off of the coast of Korea, close enough for the Republic of Korea Navy to actually go out and retrieve it. So they were able to essentially get North Korea's rocket and take a look at it and see what they've been up to up there. And it turns out they're using technology that was being used about the early 50s, or actually, excuse me, late 50s, early 60s with that there. But hey, if it ain't broke, don't fix it. So also want to talk a little bit about Boeing's Starliner, which has been further delayed with the crewed vehicle. As a part of the commercial crew program, they ended up finding 2 major issues with it. They found that some of the tape that was being used to hold some of the wiring together was actually flammable under certain conditions. So I don't know if you guys know this, fire in space, bad. So they kind of have to handle that. And then also there were some issues with the stringers on their parachutes for deployment that they have to work with as well, which frankly, doing parachutes is very, very difficult. Crew Dragon, one of its biggest problems was also parachutes as well, so this is not an isolated problem with Boeing. This is just, the physics of parachutes is really, really difficult. So everybody gets to have some problems with it. And then Vulcan from United Launch Alliance finally lit its engines.
6, 5, 4, 3, 2, we have ignition.
So a quick hot fire of those Blue Origin BE4 engines that run on methalox, so methane and liquid oxygen together. So at this point, we now are, I think, no longer allowed to make the "where are my engines, Jeff" jokes with that there. So we'll have to take a look at what happens with Vulcan. We think probably 2 to 3 months before it takes its flight. As far as we know, all the data from this, what they call flight readiness firing, looked great. And I'm very excited to see this rocket flying. This is going to be replacing the Delta IV and the Atlas V from United Launch Alliance there. And then to kind of wrap it up, just want to talk a little bit about this company you may have heard of called SpaceX.
2, 1, engines full power, and liftoff of Transporter 8. Go Falcon, go Transporter.
So this was actually on Monday from Vandenberg here in California, so you may have gone off to take a look at it. I tried to see it from here, but unfortunately the clouds did not allow me to see it. And this is that sort of stubby nozzle that they're flying on their second stages now, and I despise it. 'Cause it's just, it works, but it's an inelegant solution to what they're trying to do with it there. But of course, the beauty of a Falcon 9 is that it is reusable, and this was specifically the 200th landing of an orbital class booster from SpaceX. So you really got to think about the fact that they released a video in 2012 that had a song, that had a Muse song in it, and everybody laughed at them for that because they're like, you're not going to land rockets. You guys are absolutely nuts. Like, people have tried for decades now to have reusable vehicles, and now nobody's laughing. In fact, we're all kind of on board with that, and it's you're either going to have a reusable vehicle or your company's probably going to fail within 5 to 10 years.
And it looks like that booster has been used many times.
Yes, actually, I believe this was the 11th flight of this booster. And their fleet leader has 14 flights on it. And they are working to develop Falcon 9 a bit further so they could get about 100 flights out of each booster, which, you think about it, that saves you a lot of money. The whole point is that it's not like flying a 747 from LA to London and then ditching it once you get there. You're reusing it. You're constantly using it. So you actually get to save that money and start to really drive a profit off of launches there. And of course, speaking of launches, we've got Vandenberg, Space Force base schedule. Look at that. Everything's no earlier than June, and everything's also to be announced on their launch windows as well. So there is no concrete information about when things are launching. We do know that things should be launching. In fact, I was looking at it last night, and on the manifest, SpaceX has about 23 launches out of Vandenberg for the rest of the year, but we'll see if they're able to do that with aspects and other things. I do want to say, because someone did sort of, I don't want to say shout at me on the internet a couple weeks ago, or a couple days ago from the show, but make sure that if you are going to go see a launch at Vandenberg, that you double check the date as to when things are going to launch, because the launch dates, believe it or not, change. So aerospace, not only are we really good at doing these like bleeding edge, right on what we can do as humans in terms of machines and other things like that, we're also really good at delays. So make sure that the rocket you are going to go see from Vandenberg is actually going to launch on the day that it's supposed to. So
now, I found some footage that you didn't include.
No.
Have you seen this?
I have seen this.
There she goes.
And these are our
climbing
friends
in the sky.
At NASA Space
Hopefully to transit in front of the moon here in just about like 10 seconds.
And that's a good buddy of mine, Jack Baer.
Here we go. That's awesome.
Yeah.
Say that again,
awesome.
Jack.
Look at the exhaust. That is a gorgeous shot.
That heat distortion.
Yeah, so that's pretty cool. That takes some planning and some luck. And,
quite a lot.
Yeah. So pretty darn amazing.
That was one of their super secret projects that they were working on for that there. So I was glad to hear it. And Jack, good job. All the Topo Chico and bacon to Jack.
Well, thank you for that report, that out to launch. And now we're going to finish up the show talking about some other binary objects. This is not, by the way, a spiral from a rocket launch. Perhaps you've seen that before. Some of the Russian boosters in particular, when they launch, they will leave behind sort of a spiral trail that makes a cool feature up in the sky that looks freakish. This is being done by a pair of stars, however. There's a Wolf-Rayet star, which is a star nearing the end of its life, blowing off its outer layers, and a companion that's causing those outer layers to form that interesting pattern there. So a very, very interesting thing, but unusual, and just wanted to include it for that reason. Now, I want to talk a little bit about supernovae as well. Normally, supernovae can happen, at least type 1a supernovae that I'm speaking about here, happen when you have a core of a star like the sun that's left over after it dies. So a solar mass sun, star-like sun, expands to a red giant. So after lives most of its life, expands, goes through some phases, but eventually blows off its outer layers due to some instability. And the core that's left behind doesn't have an energy source. It's what's known as a white dwarf star. And that white dwarf will just cool over time, getting fainter and cooler and fainter and cooler, unless it has a companion. There's two ways to make a supernova out of these. You can have merging white dwarf stars where two of them merge together and they explode, because if you get more than 1.4 solar masses, well, 1.41 times the mass of the sun, what's holding up that white dwarf star can't hold it up anymore. It's known as degenerate electron pressure, if you're curious. What you can think about it is the electrons have been stripped free from their atoms. They're kind of flying around in a big soup. And you can squeeze them and squeeze them and squeeze them, and they'll pack tighter and tighter and tighter together, more tightly, until finally, due to quantum mechanical effects, you can't squeeze them any tighter. And they just say, no, you can't put any more of us here. And if you dump 1.41 times the mass of the sun in, just add a little bit more, those electrons merge with the protons and form neutrons. And you get out a neutron star. And when that happens, you get an explosion. And that explosion often reaches the same brightness, which is why type 1a supernovae are so interesting, because they can be used as standard candles. We know that they all explode at more or less the same brightness. So that's a story. Another way to do it is dumping material from a companion star. So the white dwarf used to be a bigger, more massive star. It goes through its life faster. It dies. Then the binary star that's there with it, its companion, it starts to die. It swells up. And that gas gets dumped over onto the white dwarf. And uh-oh, if that white dwarf was already at 1.4 solar masses, you add on an extra 100th of a solar mass. And that white dwarf is going to collapse and explode as a supernova. I know I say collapse and explode. You're like, well, which is it, Reitzel? Well, it's kind of both. It's a little confusing, but the central part collapses down into a neutron star, and the outer layers get ejected and making a beautiful supernova. Although I think that's the crab there they've used, and I don't think the crab is a type 1a, but I'm not sure. Anyway, moving on. So this is an example of two stars merging with the bigger star dumping on. Now, a telescope has discovered that instead of the star dumping hydrogen onto a white dwarf that made it explode, there was a pair of stars, a white dwarf, and a star that was almost entirely helium. So it had already gone through the phase where it had burned up all its hydrogen. It had formed an outer layer of helium there, and then that helium was what was dumped onto this white dwarf, forming a disk of material around it that then later exploded. And it leaves behind traces of helium, but not hydrogen. And they saw this using the Keck telescope. So I can show you some spectra here. What you're seeing here is brightness versus wavelength. So each of these curves represents how much energy you're getting at each visible, at each wavelength, so at each color. A certain amount of green light, a certain amount of yellow light, a certain amount of red light. And when they looked at this, they realized that this was a little bit of a weird-looking supernova, that it was really affected by what's known as the circumstellar material, the material that was in a disk around the star that exploded. And in fact, when they looked, I think it's on this one, yeah. When they looked, you can see that these peaks are labeled as helium, 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 helium. There's some magnesium, there's some oxygen, there's some calcium. There's no hydrogen. Why no hydrogen? So this is the first example of a helium star dumping material on a white dwarf causing a supernova. So this is a really unusual supernova that's exploded. We thought this could happen, but you have to have just the right pairing of masses and just the right evolutionary history to have this happen that way. So I don't think I need to explain that. We can move on. It's fine. I've already explained what was going on. Another pair of exploding stars that we can talk about actually were a pair of, well, anyway, I'm going to let Michelle Thaler tell this story. We have a little video I can show, and we have enough time for it. And NASA produced this, and anytime I can have Michelle Thaler, Dr. Thaler, tell a story for me, I'm going to let her. She's wonderful and does a great job explaining things. So let's just take a look at what this is about. I do need to click it, though, because I wasn't sure I was going to have enough time. So we'll get it over there, and then we'll click, and we'll see what happens. Oh, nope, that failed miserably, right? So we'll try it one more time here. There we go.
An unusual outburst about 1 billion light years away, right here, has rocked scientists' understanding of the universe's most powerful events. Some of these are the source of heavy elements in the cosmos, like gold. For decades, scientists have divided these explosions, called gamma ray bursts, into two groups, long and short GRBs. Long bursts produce a flare of gamma rays, the highest energy form of light, that last 2 or more seconds. They're thought to be caused by the black holes forming at the center of massive collapsing stars, and are followed by supernova explosions. Short bursts, on the other hand, last less than 2 seconds and are likely caused by neutron star mergers and are followed by flares of visible and infrared light called kilonovae. But a recent event has scientists rethinking these categories. On December 11th, 2021, NASA's Swift and Fermi telescopes observed a 50-second long gamma ray burst, followed by the clear signs of a kilonova. It's called GRB 211211A. It was later studied by the Hubble Space Telescope, along with a number of other observatories. Scientists don't yet know how a burst caused by a neutron star merger produced gamma rays for so long. Maybe, instead of 2 neutron stars, one of the objects was a black hole. Kilonovae are a known source of heavy elements like iodine, which was essential for the development of life on Earth. But scientists thought that they were only associated with short bursts. GRB 211211A shows, for the first time, that kilonovae can accompany both long and short bursts. After 50 years of studying these events, scientists are still learning new things about their effects on the cosmos.
Yeah, so a kilonovae is one that doesn't get as bright as a supernova, yet the energies involved are actually bigger because you're merging neutron stars to do this. And the weird thing about this object was that extra long gamma ray glow. Normally with a collapsing supermassive star that's forming this gamma ray burst, the black hole down on the inside, you have all that material from the star going into the black hole and being ejected in a jet. And as that jet pierces through the outer layers of the star, for a period of time, you'll get gamma rays. And then you'll get the supernova right after that. For a kilonova like this, you're merging these neutron stars. We expect to get a very short burst of gamma rays. And then very little. Almost no afterglow. It glows a little bit and then goes away. So it's really strange to have a combination of a long gamma ray burst and then hardly any afterglow. So how do you get the gamma ray burst? It is kind of strange. My mind goes to, maybe there was yet another companion there. Maybe it isn't just a black hole neutron star. Maybe it was a double neutron star with a small stellar companion nearby that got shredded somehow and provided some extra material for that interaction. But I don't know. This is the fun stuff with astronomy. We learn more, we uncover more, and as we do so, we find new mysteries to solve and new things to unravel. So that's how we're going to end our show tonight, with a little bit of a mystery. But thank you all for joining us here at Griffith Observatory. Thank you to our panel, of course. I really appreciate everything. Thank you, Dr. Chu, for joining us tonight. Devin Chu, really wonderful presentation. Our YouTube audience, by the way, thanks you for joining us. It said awesome talk. And we will be back on the 3rd Thursday in July. And so join us. Come on, join us here at Griffith Observatory, and or on YouTube, of course. As always, Griffith Observatory and the Department of Recreation and Parks in the city of Los Angeles bring you this wonderful program, All Space Considered. And we do thank Griffith Observatory Foundation, our nonprofit partner. And thank you to all of you out there that tune in to watch All Space Considered, and to all that joined us tonight. Thanks, everybody.